before but before I go over series, someone emailed me to go over more the question on like metric spaces. I think it's 13.15 part B. So let's just go over how to do that. I don't think it's that bad. B. Ooh, let me connect this. So, a moment. So BD is a metric space. So B is like the set of sequences, right? And we define the distance of two sequences to be I think the sup of like the largest one. Yeah. So, sup of xi minus yi. Yeah. So like x is like a sequence is like x1, x2, so on and so forth. And yeah, okay. So it's a sup over I. Yeah. So they considered F the set of sequences that have norm less than 1. So F is, I was right, it's the set of X and B. So when I write X, note it's a sequence, right? Such that sup of the components are less than or equal to 1, I think. So it's like the closed ball, sort of. And we basically want to consider whether F is compact. So we consider the open cover given by Ux. So U of X is the set of, let me say, Y in B such that distance xy is less than 1. So again, the D here is the D over here. So this is sort of like the unit, the open circle, the inside of the circle. Yeah. Inside the circle of radius 1. So, okay, and certainly x has distance less than 1 from x, right? So x is certainly in ux. So you see that, for any x, so if we union over all, x and, I guess, it's enough to union over all x and f. We need to show that there's a finite subcover. So consider F is certainly contained in union U of X for X in B. Yeah, because this thing covers B, right? I'm taking every element in B and I'm making a ball around it. So we need to show there's no finite subcover. So the one way to do this is the sequence given by xn. So this is like x1 is the sequence that is, it's kind of confusing how to write it, but it's -1 at like whatever term you are, so at the 1th term, and then you're 1 otherwise. Yeah. And then x2 is you're -1 at the 2nd term, and then you're 1 everywhere else. Yeah. And then so on and so forth. So these elements, xn, belong to F, right? For all n. To F for all n. Because the sup is less than or equal to, in fact, the norm is 1, right? Each term has norm 1. So these belong to F. Now, we have to show it doesn't belong to, they can't belong to the same UX. So suppose there exists, let's choose, 2 different numbers, right? Xi, xj, right? I not equal to j. And suppose xi, xj lie in u of y for some y. Yeah. So what does that mean? What does it mean to lie in U of y? So note that each of these are sequences, right? I mean, this is clearly these are clearly sequences. So what does it mean to lie in U of y? Well, U of y is the set of points that have distance less than 1 from y. Yeah. So I know distance xi from y is less than 1. Distance xj. This is a j. Yeah. From y is less than 1, right? By definition of being in U of y. So triangle inequality gives me this, right? Equal to y plus distance y xj. Yeah, so this triangle inequality. This is less than 1, this is less than 1, so this is less than 2. But what is this? What is this distance? We know what it is, right? I mean, this is the sup over k of like xik minus y, xjk, right? So we take all the terms and we take the sup of it, right? So remember, xi is, 1 everywhere except -1 at the ith term, right? So it's 1 everywhere else. So, ith term. And then, xj is 1, maybe -1 here, right? And then 1 everywhere else, right? So, jth term. So what is the sup here? If I take the difference, it's always going to be 0, except at the jth term, I know since j is not I, at the jth term, x, this part has a 1, right? So 1 minus -1 is 2. And you sort of see, I mean, we're taking sup, so it's at least 2. In fact, you could show it is 2, because everything else is either 0, and then it's also 2 on the ith term. So you sort of see that this is 2, right? I mean, it's enough that it's at least 2. So you see we get a contradiction, right? It's on one hand, we have to be distance less than 2, but our distance is equal to 2. So you sort of see here that like they can't lie in the same U of y, right? But now we're done because, xn for n and n are elements of f, and there are infinitely many, right? I mean, the natural number is infinite. So if there was a finite subcover, let's say, I don't know, like f is contained in union I equals 1 to n, and u of yi, yeah? Well, I have finitely many open sets and infinitely many elements, right? You can't put infinitely many into finitely many. I mean, one of our open sets has to have more than one of these, right? By like pigeonhole principle, but then the problem is, if one of them has 2 of them, that's not possible, right? We just showed no 2 can lie in the same U of y. So you see that f cannot be compact, right? So this is just counting argument. You have infinitely many things to put in the finitely many sets. One of those finitely many sets must have at least 2 of them. And we just showed you can't have 2 of them. Okay, is everyone clear on this? So any questions? Good? Okay. So let's move on to series. So this is going to be pretty boring for the first It's 15 minutes. So you have geometric series, right? Oh, before I start, does everyone know what a series is? So like sum, A, and so hopefully we all know what a finite sum is, right? So an infinite sum is a limit of a finite one. So n equals 1 to n. And we call this Sn, yeah? So a series is just a special type of sequence, right? So for example, sum 1 over n. This thing is just the limit of this sequence. So limit of sequence S1, S2, S3. But what is S1 here, right? S1 is sum n equals 1 to 1 of 1 over n. S2 is sum n equals 1 to 2 of 1 over n. Sum n equals 1 to 3 of 1 over n, so on and so forth, right? And you know how to write this. This is 1, 1 plus a half, 1 plus a half plus a third. So it's the limit of this sequence, yeah, plus a third, sorry. Why do I keep writing comma? Okay. So on and so forth, right? It's the limit of this sequence. So, and then we have special names for particular ones. So we have geometric series. In this case, it's, you know, hopefully you all know this. AR to the K is A times 1 minus R to the N plus 1. So if we sum to infinity in the case where, you know, R is, absolute value of R is less than 1, we get that it's A over 1 minus R, right? And it diverges otherwise. So diverge if absolute value of R bigger than 2. So again, diverge is, you know what it means for a sequence to diverge, right? So by diverge, I mean this, you know, the corresponding sequence diverges. So we normally call this the ratio, and this the initial term, or like starting term, right? So this is like the first case. Something's up. Let me go back. Okay. One important theorem, I'll call it a theorem. I'm not sure if it's a theorem, but if series sum an converges, limit n goes to infinity, an is 0. So this isn't particularly useful, because normally the question will ask you whether the series converges. You know, normally you don't assume the series converges, but the contrapositive is useful, yeah. So you know, i.e., if you take the contrapositive, if limit n goes to infinity, an is not 0, sum an diverges, yeah. So you can actually check if the limit of the terms inside do not go to 0, the series cannot converge, right? So of course the converse not true, right? So not true. So basically the converse is if limit n goes to infinity, an is 0, then sum an converges. And this is just not true. You know, sum 1 over n, limit n goes to infinity, 1 over n is 0, but this thing diverges, right? So that's a classic example you should have in your head. Okay, so moving on. Yeah, I'm gonna breeze through this really quick because I feel many of you know this already. So there's comparison tests. So sum an bigger than or equal to 0 for all n. Basically, the first part is if the big guy converges, the small guy does, right? So absolute value Bn is less than or equal to An for all n, then sum Bn converges, right? So yeah, so if Bn is a small guy, right? The big guy doesn't go off to infinity. The small guy can't go off to infinity, right? But and then vice versa, if the small guy goes off to infinity, So let's make an the small one, i.e. diverges, right? Another way to say is diverges. Bn bigger than or equal to an for all n, then sum bn equals positive infinity. So normally a sequence diverging doesn't mean infinity, right? Like a sequence can not exist in many ways, but in our case, all our terms are positive, right? Right here, positive, right? So if we sum a sequence of positive things, our partial sums can only get bigger, right? Because we're only adding more and more positive terms. So, and you had a theorem before saying monotonic sequences, right? They either converge or they diverge, right? Or they diverge to plus minus infinity. Well, it can't diverge to minus infinity because everything's positive. So if you diverge, it's going to be plus infinity. So, okay. So I think I'm not going to go over this, but integral tests also needs positive terms. So there's a notion of, okay, what if my terms are not positive? Then we take absolute value. So basically, a series converges absolutely. So a series sum an converges absolutely if and only if if you take absolute value, the absolute value converges. And it's a theorem that says absolutely convergent series converge. So this is useful because, right, because you can't really use comparison tests and integral tests unless things are positive. So it's nice to just to make it positive, you take absolute value. So, okay, so let me just go over 2 more tests and then we'll go straight to the, to some examples. This one might be unfamiliar to people. It might look strange. So sum and sum of non-zero terms. Right, so we have I. So the non-zero terms doesn't really matter because if it's 0, it contributes nothing to the sum. So you could just throw it out. So converges absolutely if lim sup of an plus 1 over an is less than 1, and it diverges if lim inf, so this n goes to infinity, right? So of an plus 1 over an is bigger than 1, and then otherwise no info. So I'm sure you all are used to just, so in the case the limit exists, lim sup is equal to lim inf, right? So and that's your usual math 2b ratio test, right? Like limit of the ratio is less than 1, converge, limit of ratio is bigger than 1, diverge. Yeah. But in general, you don't know whether the limit exists. So we can't write limit. Okay, so we have root test. This is the last thing I'll go over. So sum and series alpha is lim sup of an to the 1 over n. Then this is alpha, yeah. Then sum an I converges absolutely if alpha less than 1, diverges if alpha bigger than 1, and otherwise no info. Yeah. So again, I'm sure you are used to the lim sup being a limit, but we don't know a priori whether the limit exists. So we have to write lim sup. Okay, any questions so far? If not, we could go straight to example. Okay, so I'm just gonna, because I'm sure you all know how to do this. So let's just do 14.1a. Let's start off easy first. So 14.1a is n to the fourth over 2n. So I don't care. I mean, it could start whatever. So, I mean, one thing is, if you see, like, let's use ratio tests. So let's check the lim sup of n plus 1 to the fourth over 2 to the n plus 1 times 2 to the n over n to the fourth. So this is, I mean, these cancel, right? This cancels the 2. So this is just this, right? N plus 1 to the fourth over n to the, and in this case, sorry, lim sup. In this case, you know the limit exists, right? Because this is just at this point, you know what this limit is. It's a half. Okay, so in this case, the lim sup is the limit. So in the case the limit doesn't exist, you have to use that lim sup definition. Yeah. And this is less than 1, so it converges. Okay, let's move on. Let's do f. Yeah, so sum n equals 2 to infinity log n. So I'm just going to assume for simplicity log is base e. Yeah, just for simplicity. So log n equals ln n. I mean, if not, you can just base change. Yeah, it doesn't really matter. So we need ln n. So again, we need to start at 2 because ln of 1 is 0. And you can't divide by 0. So any ideas on how to do this? Not too bad. But okay, so I mean, there's just comparison tests. Yeah, so ln n is less than n. So 1 over ln n is bigger than 1 over n. So this is bigger than or equal to sum. But this is a small guy, and this is the big guy. But small guy goes to infinity, right? This diverges because it's harmonic series. So this diverges, right? I mean, like, it's true that x is bigger than ln x, right? Hopefully that's clear. If not, just draw the picture proof. If you graph y equals x, it's a line. If you graph natural log, it's like this, right? So it's pretty clear that the line is always above the natural log. Okay, so this is by comparison, right? Diverges by comparison. Test. I'm gonna go write the problem. Some sine of n pi over 9. I don't know where it starts, but let's just say it starts at 1. So, any ideas on this? Anyone? Yeah, just say converge or diverge. Or like, yeah. Nobody? So, it's the thing I wrote earlier. Where is it? This thing? Yeah, if the limit of the terms don't go to 0, we diverge. So this thing, what is this thing, right? This thing, sine is 2 pi periodic, right? So I have sine of pi over 9, sine of 2 pi over 9, all the way to sine of, let me think, 18 pi over 9, right? And then I have sine of 19 pi over 9. But this thing is the same as this, right? Because where sine is 2 pi periodic. So you see, we sort of only have 18 terms. 18 terms, and then repeat the 18. And then repeat. And then so on and so forth, right? So that is our sequence. So if we have a bunch of repeating terms, the only way it's going to go to 0 is if all the terms are 0, right? Because if not, you know, like, you could, no matter how far you go in your sequence, there's always a term that's, you know, at least somewhat bigger than 0. So, but you see here, not all the terms are 0, right? Sine of 2 pi over 9 is not 0. So you sort of see that this thing is, in fact, it does not exist, right? You don't even know it does not. You just need to know it's not 0. So for people who are bad at math 2A, it's not 0. So the sum diverges. Yeah. Okay. So let's just do one more, and then we'll go to more proof-based stuff, because I feel, you know, this is math 2B. Let's do n factorial over n to the n. Yeah. Okay. So if you see a factorial, chances are you want to use ratio tests. So let me just say ratio test to get rid of factorial. So let's use ratio. Lim sup n goes to infinity, n plus 1 factorial over n plus 1 to the n plus 1, right? So how do these cancel? So how does factorials cancel? This is the first thing you should know. So just try it out, right? Like if I have 7 factorial over 6 factorial, you can check this as 7. So why? Because 7 factorial is 7 times 6 times 5 times 4. 6 factorial is this, right? So you see almost everything cancels. So in general, n plus 1 factorial is n plus 1 times n factorial, right? So you see this cancels to n plus 1. And then we could cancel this to make it n. Yeah. So this is just lim sup n over n plus 1 to the n. Everyone good so far? So I'm gonna put 1 over. Yeah, so this is you know, lim sup lim sup. I mean, because I'm sure you are all, you know, if I just divide by 1, I could flip the thing. Yeah. So here, the reason I wrote it like this is because if you long divide, right? If you long divide the bottom, this is the same as 1 plus 1 over n to the n. Yeah? I mean, just 1 minus n, 0 plus 1, you know. So you get 1 plus the remainder over, you know, Hopefully you all know how to long divide. But what is this limit? What is the bottom? What now I can just write limit because this is what where does 1 plus 1 over n to the n go to? What? Yeah, the previous ones diverge. Yeah. But where does 1 plus 1 over n to the n go to? Math 2a. So anyone? So okay, maybe I need to review math 2a. This goes to e, yeah? The bottom goes to the number e, and e is like 2 point something, so this is smaller than 1. So this converges, yeah. Converge. Do people know this, or can I move on, or should I go over why it's e? Okay, so to calculate this limit, instead I'm gonna calculate the natural log of it, and then whatever answer I get, I'm gonna bring it back, right? So if I natural log, since this is continuous, I could exponential my answer to get back the limit of this sequence. But the nice thing about natural log is this thing is n ln 1 plus 1 over n. The property of natural log lets me bring the n down, like any power. And multiplying by n is the same as dividing by 1 over n, right? So multiplying, for example, by 2 is the same as dividing by a half, right? So, okay, but here, this thing goes to 0. This thing goes to 0, right? Because 1 over n goes to 0, so it goes to ln 1, which is 0, and the bottom goes to 0. So L'Hopital gives me that I take derivative on top and bottom. Now, the top goes to this, right? Times chain rule the inside. The derivative of 1 plus 1 over n is just derivative of 1 over n. Now, I'm just going to leave it like this because the bottom also has a derivative of 1 over n, right? L'Hopital. So these just cancel. I mean, you could write it out, but the point is they cancel. So this goes to 1 over 1 plus 1 over n, which is 1, right? But this was the limit of ln of the sequence. So if I exponential both sides, I get e to the 1, right? So I get e, yeah. That's the fast way of, proving it. So is everyone good with this? Yeah. Yeah, just review your math 2a. Okay. So let's go to proofs now, because I feel that that's more important. So I'm going to do 14.5 first. So these are now proof-based problems. So sum an is a, sum bn is b. So we have that it converges, right? So our sums, let's just start at 1 for simplicity, is a, and sum n equals 1 to infinity, bn is b. A, b real numbers, right? So a, we want to show sum n equals 1 to infinity, an plus bn is a plus b, yeah? So let's unwind this definition, yeah? So sum n equals 1 to infinity, an plus bn is just limit n goes to infinity, this, right? Now, here, I'm using the fact that for finitely many things, limit of sum is sum of limit, right? Provided it exists. So here, this is, if you like, this is A1 plus B1 plus A2 plus B2. So what I'm going to do is I'm going to rearrange everything first. So here, all the way to AN, or A capital N plus B capital N, right? So I could move everything and make it, this is limit n goes to infinity, sum n equals 1 to n of an plus sum n equals 1 to n of bn. Yeah, so I'm just rearranging terms, right? I'm using the fact that like b plus c is c plus b. I keep swapping terms. And I could do this because there's finitely many. There's only up to capital N. So, and now we use the fact that limit of sum is sum of limit if limit exists. But we're given the limit exists, right? We're given that these limits exist. So we could, bring the limit, use this property to say this is plus and by definition, this is, so you get A plus B. Yeah? Everyone clear on this? So it's just limit law. So let's move on. So for part B, K is an R, and I want to show sum KAN is KA. Yeah, K times A. So sorry, again, N equals 1 to infinity. So again, everything's just definition. So what is this? So this is limit n goes to infinity, sum n equals 1 to n k a n. So now I could pull the k out. Now, why is that true? So this is true. This is just distributive property, right? Distributive property, right? So distributive property says k times a1 all the way for finite, right? For finitely many things, I could FOIL the k inside, right? So I'm sort of going backwards. I'm going from here to here, right? So I'm FOILing the k out. This is just distributive property. And you have a thing that says you could pull the k out of the limit because k is a number, right? That's one of the limit laws. And here the limit exists, right? This is just, infinity an, which is k times a. Okay, is everyone good so far? We're just using definition of what an infinite sum is. Yeah. So, okay, let's do part C. So, is AN BN AB? So here, what you're gonna see is if you write out the terms, it's not. So why is that true? Because sum AN BN is what? N equals 1, 2. If you write it out, it's A1 B1 plus A2 B2 plus A3 B3. Now AB on the other hand is this, right? This is A and this is B. Yeah, so if you think of, you add infinitely many numbers, right? A is what? I'm summing A1 plus A2 plus dot, 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 right? Let me just write A3 for, just to, times B1 plus B2 plus B3 plus dot, dot, dot. So we certainly have every one of these terms, right? I can multiply A1 with B1, A2 with B2, A3 with B3. But you see that the top one is missing terms, right? Because here I have A1 times B2, right? Here I have terms like A1, B2, A2, B1, so on and so forth, right? And here we're sort of missing that. So you sort of see where it's not equal. In fact, the top one is missing tons of terms. So is everyone clear on this? So this is sort of like the point is here your indexes have to be the same, and here your indexes could be different. Like it could be AI BJ, while the top is like AI BI. Everyone good with this? So okay, I'm gonna do 14.7. So prove that if some AN is convergent series of non-negative numbers and P is bigger than 1, then AN to the P converges. So, so 14.7, some AN converges and AN is positive. So AN is bigger than or equal to 0. So want to show some AN to the P converges. So this idea is the same as the top. So what can anyone take? Obviously, this is true, right? If I raise the series to the P power, it's bigger than some AN to the P. Yeah, everyone good with that?
Yeah.
So what do you know? So here, why is this true? Because again, if you write out the terms, let's write out the right-hand side, yeah? This is A1 to the P plus A2 to the P plus A3 to the P, so on and so forth, right? But some AN, it's A1, I'm raising it to the 8th power, right? So I'm sort of multiplying P times, right? So this should be A3, yeah? So I'm multiplying, P times. And the same argument applies, right? I can get A1 to the P by, multiplying every A1. And I can get A2 to the P by multiplying every A2. But the top part is missing terms like A1, A2 to the P minus 1, right? It's missing like many terms, right? Like the terms in by FOIL law, it's missing a lot. So you see that, and this one's bigger. And in general, it might not be if your terms are negative, right? Because it could be the terms, the top one's missing is negative, so it's actually smaller. But here we assume it's all positive. So we certainly have is bigger than or equal to this. And since all terms are positive, this is true. Okay, but then we are done, right? We have some AN to the P, right? If I go, n equals to, it's the limit of this sequence, right? N goes to infinity by definition. And this Sn is increasing, right? Because things are positive, right? I mean, if I keep adding more and more positive things, it's increasing. So I have Sn increasing, Sn bounded, right, by some AN to the P and 0. So what can you tell me? I have a monotonic sequence that is bounded. There's a theorem that says it converges, right? So again, bounded monotonic sequences converge, right? And you're done. So Is everyone good with that? So again, I guess I'm sort of, we assume this converged, and so it's certainly true that the p, if I do it p times, it converges, right? So what I'm using is, using p times, if limit n goes to infinity, Sn is S is T, then limit n goes to infinity, Sn Tn is St. But in this case, my Sn and Tn are the same. So I'm using it p times, right? Because I'm multiplying. This is like I'm using it p times. So right, because I'm multiplying it everything p times. So I'm using product of limit of product is product of limit, if you like. Okay, everyone good so far? It's this limit law. Okay, let's do one more. Let's do it like an even one. Let's do 14.6. So A, prove if some AN converges and BN is a bounded sequence, then AN BN converges. So some AN converges, BN bounded. So what does it mean for BN to be bounded? It means absolute value of BN is less than or equal to M. Yeah, for some M. So want to show some AN BN converges. Does it tell me? Oh, sorry, some absolute value. Yeah, should be absolute value. That makes more sense. Okay. And we want to show this converges, yeah? So first, we have stuff on the absolute value. So let's take absolute value, yeah? So we're going to use absolute convergence, right? So again, recall absolutely convergent series converge, right? So if, i.e., if this converges, verges, then the original converges, right? That's what absolutely convergent series converge means. So we just need to show this thing converges. But why do we like this now? Everything is positive, so we can use comparison tests, right? Comparison tests, since everything's positive now, I could compare. So this thing is less than or equal to some M times absolute value of AN, right? Because BN's less than, absolute value BN's less than or equal to M. So by the problem I just did, where is it? This one, right? Basically, I could pull the K out of the sum, right? If I pull the K out of the sum n equals 1 to infinity, AN is A. So this, I basically showed above that like I could pull constants out of the sum. So this thing is equal to M times some absolute value AN. But then this converges, right? So, I mean, obviously this means, this thing converges, right? Because, I mean, if the sum converges to like A, that thing converges to M times A, right? That's what I proved above. So the big guy converges, so this converges by comparison test, right? And then again, let me just write it out. So sum A and BN converges as it converges absolutely. Yeah, Everyone good with that? Great. Hopefully that's all I have for today. So hopefully it's not that bad. So your quiz is on series, obviously.